we are going to talk about the acid-catalyzed bromination of an aldehyde or a ketone. When you do this, the halogenation is very specific toward the alpha position, and it will always go there. The nice thing about doing it in acid is it stops at one halogenation, whereas if you do this in base, it may continue to go on and on and on. So if you want just one halogenation to occur, try doing it in acid. And the neat thing about this particular type of chemistry is you produce acid in the course of the reaction. So it auto-catalyzes itself. It continues to help itself perpetuate. You just need a very small amount of acid in the very beginning to make this occur. So the first steps of this mechanism are exactly the same as the acid-catalyzed enol formation from an aldehyde or a ketone. And I'm going to use the exact same aldehyde we had a moment ago and go through those steps very quickly, the same aldehyde I've been using for these other mechanism videos. So the conditions that you would see if you were talking about doing a halogenation at the alpha position is you would have the halogen on the arrow. Now, these aldehydes or ketones do tend to be liquids. They tend to be that themselves, but this is what you're going to note on the arrow when you do this. They may have a little bit of acid present, but there isn't a whole lot you need to worry about in that respect. You also would need to have some sort of an organic solvent in case these are solids. It is a possibility. There is going to be a little acid here as well. So initially, what happens? Well, your acid source, you will use an oxy acid, by the way. You will use it to protonate the carbonyl oxygen, just like we did as we went to the enol before. And by doing so, you're going to have resonance stabilization of the positive charge on the carbonyl carbon and the carbonyl oxygen. Oops. Now the resonance structure on top is the predominant resonance structure because everyone's got an octet of electrons there. The one on the bottom, the carbonyl carbon, does not have an octet, so it is a minor contributor to resonance. But it is a contributor. Now what happens at this point is that the water that is present when you add the acid source will come in and remove a proton on the alpha carbon. So again, I'm going to draw those in green. This is exactly the same mechanism you saw for acid-catalyzed formation of the enol. So water removes the proton, and you take this pair of electrons, give it back, and you break the pi bond if you're using this resonance structure. If you're using the other one, take the proton on the alpha carbon, give the electrons back, make the pi bond. Okay. And we're going to end up, at the end of the day, with this enol. So that's exactly the same as what we've seen previously. Okay. Next, this pi bond acts like other alkenes. It's a source of electrons, and it's going to act as a nucleophile toward the bromine that is in solution. You can do this with chlorine as well. But this is very much like what you've seen with alkenes and other halogens, except it doesn't form a tetrahedral intermediate. And the reason it doesn't form a tetrahedral intermediate, the tent, doesn't form the tent. The reason it doesn't form the tent is because this still is not an alkene. It's an enol. It's an asymmetrical double bond. There is a pull on this pair of electrons because oxygen is attached to one of the carbons in this double bond. So we don't form the little tent. So what we are going to do is this pair of electrons is going to be used as a nucleophile. You do add it to one of the two bromines, and it doesn't matter which one. As bromine gains electrons, you break the bromine-bromine bond and give the other pair to the other bromine. Now, in this case, you do care about which of those two carbons of the double bond picks up the bromine. There is no tent. And it will be the one that is not attached to the oxygen. That's very important. It's going to go to the alpha carbon. And the reason for that is due to the product that you get. It has resonance stabilization of the positive charge. If you made the tent, there would be no resonance. And resonance is always better than no resonance. And this is why we give it to the alpha carbon. I'll draw on the hydrogen so you don't forget that it was there. I didn't draw that right. Sorry. Now this intermediate that you see, it does have a resonance structure. You can break the pi bond and give those electrons to the oxygen. And by doing so, you've got a positive charge on the carbonyl carbon. So as you look at those two resonance structures, the one on the left is the predominant resonance structure. And that's due to the fact that with that resonance structure, everybody's got an octet. The one on the right, the carbonyl carbon, does not have the octet. So this is where you are for a moment in time. You are then going to remove the proton from the oxygen. We also have water in solution. And it will come in and you can remove the proton from either of these two resonance structures. Doesn't matter which one you want to do it from. If you do it from the first one, just give the electrons directly to the oxygen as you take the proton. If you do it from the one on the right, give that pair of electrons to make the carbon-oxygen double bond. And as you can see, we have generated acid during the course of this reaction right here that will help catalyze more of this. The neat thing about this is that we are very specific in our bromination for the alpha position. This could be very useful to you if you maybe have a tertiary carbon somewhere else and you couldn't do free radical halogenation, or if you wanted to target maybe, like I did here, a secondary carbon and maybe there were other secondary carbons. You can be very specific for the one that's right next door to the carbonyl carbon and not have the halogen adding as a nucleophile to the carbonyl carbon or anything like that. And the neat thing about doing it in acid is it stops at one addition. So these are all very good things for synthesis to be aware of.